In this lesson, we're going to develop a simple model for a brushed DC electric motor, a motor that you likely have seen in your childhood if you ever took anything apart, a motor that might look like this in some kind of electrified toy like a car or maybe a Lego set. If you would take that apart, you would find that inside you would see this type of construction. A DC motor, a brushed DC motor, has the following key components. Okay, it has some permanent magnets called the stator magnets. It has an armature that is attached to a rotor, or actually this whole assembly, I guess, is called the rotor. It's the portion of the motor that actually rotates, and attached onto the rotor is the armature along with some windings. And those windings are terminated onto a commutator, which is this surface, this electrified surface that conforms to the shape of a cylinder and has subsections. The number of sections as you go around one full revolution on the rotor is a function of the number of poles that a motor might have. These surfaces, these commutator surfaces, are the means by which the external terminals, right here the plus and the minus, are connected ultimately to the coils that are part of the rotor. And brushes are used to make that electrical connection. So those brushes are formed so that they ride smoothly over the commutator surfaces, and there is a low resistance between that. And as the motor turns, you can see that the brushes will make electrical contact with different portions of the commutator surface, and therefore, because those commutator surfaces are ultimately connected electrically to different portions of the windings that are on the rotor, the rotation of the rotor leads to a commutation or a switching of which windings are electrified from the external circuit connected here as the rotor makes a full revolution. And we'll talk a little bit more about that toward the end, but as you can see, the complexity of the motor is such that it takes some time and consideration to kind of get our minds wrapped around that. So in order to make the concept of a DC brushed motor more accessible, we're going to begin or we're going to focus on a single coil motor, which is depicted here in this diagram that you see to the left here. This diagram actually has or shows no commutator. Now rest assured, in the end, our DC motor, even this simple single loop DC motor, is going to have a commutator, but in this diagram we're not showing it. We simply show two rings, slip rings, that over the full revolution of the rotor, the external terminals, which I'll say plus here and we'll say minus here, are continuously connected electrically to either end of this single loop. Okay, so I'm going to label a couple other things here before we get started. I'm going to label an axis of rotation. Well, we know that it rotates, axis of rotation is right here, but I'm going to label our angle of rotation. We'll call that theta, right here. Maybe I should make that yellow. Okay. And what else do we need to... Okay, and then we'll have omega, which is going to be defined as the time rate of change, like delta theta over some delta time, or we could write it differentially as d theta dt. Okay, so omega m, or omega, here is our angular frequency. Maybe I'll put M. I'm used to putting an M for motor. Okay. All right, so what do we have here? We have two permanent magnets, or two magnetic poles, and these two magnetic poles create a fixed magnetic field, which we will label as B naught. Magnetic field is going to be B naught. And we also are going to label the length of this wire here as L. And we will also, for convenience, we will say that the width of this wire is, boy, it's hard to see that. Let me change this to something more visible. Okay, the width, we'll also call it L as well, just for simplicity. This can easily be changed if your particular coil is of a different dimension. Okay, the area is going to be A, and that will simply be equal to L squared. And then lastly, we're going to have a current I that is going to flow. So we've defined L. This is side and length of coil. We have B naught, which is the DC or constant stator magnetic field. It has units of Tesla, by the way. We have theta M, which is the angular displacement of the rotor, or we could say coil. Okay, and then we'll call this I coil. I coil is the current flowing through the coil. Okay, and then I'm going to add another one here. Let's see, we will say V coil. Okay, V coil is the, I'll say external, we'll clarify this later, external coil voltage. And this is really equal to the motor terminal voltage. Which we often will use when describing the electrical input to a motor. So VM, so in other words, VM and V coil are synonymous. Okay. That's why, let's say, are equivalent. Okay, and then let me add another one. Let's see, what else do we have here? We'll add one more N coil. This is going to be the number of coil turns. Okay, now the diagram shows only one turn, but to make it more interesting and more realistic, we're going to put multiple turns on this coil, so it would just loop around and around and around like so, with either end ultimately coming out to the slip rings and connecting externally. Okay, so these are our parameters for this motor. Now before going any further, I'll just tie this back to the actual brush DC motor. And in the brush DC motor, what we have is we have more than one coil. We may have 2 coils, 3 coils, or more. And these would be equally spaced angularly about a full revolution. So if we had two coils, we would have one of the coils, the one that's shown here in our simple diagram, in the theta m equals 0 plane. And if we had a second coil, we would place that second coil in the theta m equal 90 degree plane. If we had three coils, then they would be dispersed between 0, 60, 120. Okay? But again, we're going to leave that off for now. We'll come back perhaps at the end and explain what the advantages are of having multiple poles and multiple phase windings in our DC motor. But we can capture the full principle of operation of this motor by just considering one coil. Okay, in order to develop the physics of a DC motor, we need to consider a couple electromagnetic principles from UPhys. We will make use of Ampere's law, Faraday's law, induction, Lorentz Force, and Lenz's law. So let's review these briefly. Now, Ampere's law relates current to magnetic field. Faraday's law of induction relates voltage to time rate of change. We can say delta B over delta T or dB dt. Lorentz force relates a force to acting on a conductor to the current that is flowing through the conductor, the length of the conductor, and also the magnetic field that the inductor, or that the wire, sorry, say inductor, I mean wire, that the wire is immersed in. And then Lenz's law tells us the polarity of induced voltage in a coil. Okay, now let's look at how these laws apply to the functioning of our motor. We're going to look at the induced voltage in our coil, and then we're going to look at the induced torque on the coil. So consider this simple diagram here where I'm showing the coil that has been rotated some degrees theta m positively and is exposed, if you will, to this DC magnetic field B naught that is passing through that loop. Now, the total flux that is passing through that loop is going to be B naught, let me draw my angle again, theta m, and if we have a length of L, the flux, recall that flux phi is equal to the magnetic field times the effective area. Now in this case, if the coil was at a theta m of 90 degrees, the entire face, or the face of the normal to the loop would actually be parallel with B naught. But in general, it's going to be at some angle that's not going to be lead to a full facial exposure to B naught. And so phi is going to end up being equal to B naught times A, which is L squared. Remember, because the sides of our coil are L and L, times, and now we have to think about it's going to be a sine or a cosine. It'll turn out to be a sine theta m, because when theta m is equal to 0, there is no magnetic field lines passing through the loop. When theta m is 90 degrees, then we have a maximum number of field lines that are passing through the coil. Okay, so this is our flux here. Now Faraday's law says says that the voltage that's induced in the coil is equal to minus N, the number of turns of the coil, times the time rate of change of the flux passing through the coil with respect to time, d phi dt. I guess I'll write this as coil there. Now I'm going to label this voltage out here as V coil. And what we're going to say is that V coil is equal to, now I'm going to take N coil times, and I have to take the derivative now of my phi of coil. Now one thing I do need to be careful about, oops, is that theta m is equal to the angular frequency omega m times t. Okay, so at this point we don't yet have, without that description, we don't have a relationship between how phi changes, or what phi is as a function of time. So we need to relate theta m to time. Okay, so now when we take the derivative, we're going to have an omega m that's going to come out front. We'll have b naught L squared, and then we'll have a cosine of theta m, or omega mt. I'll just write theta m here. Now I've left some room out front because I don't know if there's a minus sign or not. We need to be careful about this. It's true that Faraday's law says that that there is a minus sign, but there are some conventions assumed there. And in this case, I've already labeled the plus and minus signs on my coil. So I need to determine whether or not for my labeled V coil, do I have a plus or a minus sign. So we're going to appeal to Lenz's law, use Lenz's law to determine sign. Now, Lenz's law says that the induced voltage in a coil will be such that if the coil circuit is completed, in other words, you provide a closed path for the current to flow, the current that will flow as a result of the induced voltage will be of a direction such that it will tend to cancel the change in magnetic field. So in our case, as phi m is increasing, our coil is rotating counterclockwise. The magnetic field is increasing as it enters to the left, from the left side. Okay, so the induced voltage is going to be such that the current that will flow if we complete the coil circuit will actually produce a canceling field that will point this way, I'll say Lenz. Okay, so what direction of current will produce a magnetic field that will point to the right? Well, that will be a current that will flow like this. Oops. Let me try that again. I'll call this I Lenz. Right? Do the right hand rule. And so you wrap your fingers, your four fingers around in the direction that the current is flowing, and your thumb points to the left. Okay? So what kind of voltage, V coil, will lead to a current flowing in the I Lenz direction? Well, based on the polarity defined here for V coil, it's actually going to be a positive V coil. Right? If I go and I connect, say, if I close this circuit, so I have some resistance there, well then the current that's going to flow, because V coil is positive, okay, this is going to be I direction for a V coil greater than 0. Okay, so when V coil is greater than 0, the current flows in this direction as indicated by I Lenz. That I Lenz current produces a B Lenz that points to the left and opposes B naught. So therefore, in my expression for the induced voltage V coil, we're going to have a plus sign. Okay. Now one other thing I'm going to do is I'm going to change this to E coil. I will explain that further later, but essentially E coil is going to be used, E is going to be used for the induced voltage, which is generated from the Faraday's law, from the Faraday effect, whereas the actual terminal voltage at the terminals of the motor, which we will label V coil, could actually be different from that. And the reason for that is that our coil, that so far we've assumed to be an ideal coil, will certainly have some resistance, and it may have some inductance as well. And so V coil and E coil will not always be the same. Note that when I coil is equal to 0, then V coil, the external voltage, external motor voltage, will be equal to E coil. And that's what we have in this case. There's nothing connected to this coil. And so if we simply were to measure the voltage at V coil, we would find that this voltage would precisely be predicted by Faraday's law of induction alone, which is N coil times omega M times B naught times L squared times the cosine of R theta M, or omega MT. Okay, now we can move on to the second piece, which is the induced torque. So there's going to be, if we're running, so the first case, we really could think of running the motor as a generator, where I come along and I start spinning the shaft, and we measure what comes out of the on the coil at the terminals. In this case, now we're going to look at, if we apply a current through our coil, what kind of torques are induced on our rotor and show up at the output of our motor shaft. And to answer this, we need to use we're going to need to use Lenz, the Lorentz force. Okay, the Lorentz force says that the force acting on a wire is equal to, we can write it two ways: Q, the charge on an electron, V, which is the velocity of that electron, cross product with the magnetic field B. I can also write this as I, the current flowing through that wire, times L, and cross that with B naught. Okay. Now notice in this case that L, right, our little L direction, well, I'm putting, maybe I should do it this way to be a little more, I think, proper. We'll say I coil times the scalar L, capital L, times our direction, little l, cross B naught. Okay, so this is just our unit direction. And L and B naught are at 90 degrees. Okay, they're normal to each other. Therefore, L cross B naught is just going to be equal to B naught, right? Because L is our unit. Maybe I should really be careful. Let me rewrite this. Since I labeled the length little l before, I'll say U subscript L. There we go. So we'll have L times U sub L is just going to be equal to L times B naught. So therefore we can write that the force is going to be equal to I coil times L times B naught. And we have to also include the fact that we have N coil turns. Okay, so if I have this force, the force on one wire will be I coil times L times B naught, but because I have N coils, then I have to multiply this force times N. And furthermore, I have to multiply it times 2 because there are two sides. Okay. Now, which direction is this force pointing? Okay, this force, if we do the cross product, the force is going to point directly up. This will be force, and it'll point directly down. So let me put this F over 2 and F over 2 as I have labeled it here, F. Okay. Now the actual torque that is going to be induced in this coil is going to be a little different from this. Now the torque in the coil will be equal to F. However, notice that F is not, maybe I should draw a diagram here. Here is theta M, and I have a force acting up here, F over 2. And the actual force that contributes to a torque is going to be this force here, which is F over 2 times, what will it be? Cosine, right? Cosine of theta M. And so we will have that the torque in the coil will be equal to this length here is L over 2, right? So the torque arm is L over 2. L over 2 times F over 2 times cosine theta M. And again, because I have two sides, I'm going to have that same force acting over here as well. And now we can clean this up. The torque in the coil is going to be equal to, let's see, L over 2 cosine theta M times the force, which the force is going to be 2 I coil L B naught N coil. The 2's cross out, and I can combine the L's as L squared, or the area, B naught N coil times I coil times cosine of theta M. Now let us go back and recall our voltage induced in the coil. Place this here, and oops. Let's see what we have in common here. I'm going to rewrite this, noting that there's an L squared, there is a B naught, there's an N coil, and then there is omega m times cosine of theta m. So I can get rid of this and replace it with this same statement. But I note that this term of constants are the same. L squared, B naught, N coil. And so we're going to give this a name. We're going to define a motor constant. Call it K. We'll call it Km. Sometimes it's called KB. And it is defined as N coil times L squared times B naught. Then tau coil and E coil become, and we can write tau coil is a function of theta m, and it will be equal to Km times I coil times cosine of theta m, and E coil, which is also a function of theta m, will be Km times omega m times cosine of theta m. Let's look at some plots of the tau coil and E coil for a sample motor. Here is a very, very small DC motor. I've listed the parameters here, typical parameters. And what we're going to assume is, well, in this case, we're going to be operating at a constant coil current, and we're going to look at the coil torque, and then we're going to operate at a constant motor angular frequency, and we'll look at the E coil that is generated. We're plotting this as a function of theta m. So again, recall that theta m, let's see, 0 degrees here, and we have the motor that is, the rotor that is rotating clockwise here, and we have our B naught coming from the left here, and we have current going into the page here, I coil. Actually, it's N I coil times N coil, and then we have current coming out of the page right here. Okay. Notice that the torque on the coil is maximum when theta m is at 0 degrees. Okay, that corresponds to the coil being in this position here, and when you do IL cross B with the B pointing to the left, we get a torque F that is going straight up, and force up, force F that's going straight up, and a force that points down, going straight down, and these are at 90 degrees. The torque arm and the force due to the Lorentz, basically the Lorentz force, and so we have maximum torque right here when theta m is at 0. Oops, sorry, right here. Pointing to the wrong plot here. There we go. Now we have, second case is when we arrive at, say, plus 1/2. So this is pi over 2. Okay, this is pi over 2. This corresponds to the coil pointing this way, we have still have B naught pointing from the left. We have an angle of pi over 2, and now the force, the force that is acting is pointing up. It's still F over 2. This is pointing down F over 2, but the torque, the net torque, is 0. And the same is true if we go over here to minus pi over 2. Okay, so there's a region where the torque is going to be maximum, and that's going to be when the coil is horizontal. Its plane is when the magnetic field is in plane with the plane of the motor or the coil. It's going to be minimum when the B field is normal to the plane of the coil. Similarly, we have voltage that's going to be induced in the coil, and this voltage will be maximum at theta is equal to 0. And again, that's because at that point the magnetic field or the flux passing through this coil is going to change maximally. At this point here, actually B in the coil, I'll say B coil, is equal to 0. Okay, but B coil dt is equal to maximum at that point, because it's going from 0 to now it's going to be increasing. So a couple conclusions from this is that at theta m equal to 0 is where we can achieve or transfer the most torque to the motor. It is also where the coil induces the maximum, what we call back EMF. EMF is electromagnetic force. It induces the maximum induced voltage when the rotor is at 0 degrees. Now, to make this a little more practical, we need to return to our basic assumptions for our coil and augment them a little bit. So we want to return to our coil model. And what we're going to add to our coil model is we're going to add some resistance. Our coil, and we haven't actually drawn a schematic yet of what's going on here, but I'm going to go ahead and start doing that. I'm going to draw a dependent voltage source. And this voltage source is going to be the E coil. Okay, so I'm trying to capture a simple model for the electrical side of our motor. And what we've noted so far is that as you spin the coil, voltage is induced at the terminals of that coil. And so that is like a voltage source. And so we're going to capture this. This captures the induced voltage. And it's equal to KB, or Km times omega m times cosine omega mt, or theta m, however you want to write that. And to this point, in these plots above, we assumed that we were forcing some kind of coil current through our coil. But in reality, what we're more likely to be doing, if we're going to be powering our motor, is to be supplying a voltage V coil. Maybe we'll tie this to some battery. Right? And there will be a resulting volt current that flows as a result of the V coil being applied. But we won't directly control what I coil is. Instead, I coil will be equal to whatever voltage we apply externally to the coil, or to the motor. Call that V coil or VM. And we'll then subtract whatever voltage is induced in our coil due to the Faraday's induced induction. And the difference between these two voltages is the voltage that's across the resistance of our coil. And that's what's going to drive the current that will flow through our coil. So in this next plot, here we have coil current, coil current versus angular position at a constant voltage V coil of 1 volt. Okay, so what I'm plotting is I coil now is actually a function of the angular position, and it is equal to V coil over R coil minus E coil, which E coil is Km times omega m, all of that all over R coil times cosine of theta m. And we find now that the current flowing through our coil is actually maximum at pi over 2 and minus pi over 2. And why is that? Because at pi over 2 and minus pi over 2, remember that the induced voltage, right here, the induced voltage is 0 at this point. Right? So when there's no induced voltage, at these points here, all V coil appears across our coil. Okay. And at this point here, at theta m equal to 0, we have a minimum current. The current there is going to be determined by V coil minus Km omega m, all of that over our coil. Because at theta m equal to 0, remember that's where we get the maximum induced voltage across our coil. So another way to consider this is if I drew a line here, and this is my V coil, okay, then the actual current that flows is going to be always due to the difference between the V coil that I apply externally to my motor and the induced E coil that is going to be induced within the windings of my coil. And the difference between those two is going to be R coil. VR coil, sorry. That's what this voltage is. And you see that it is minimum when we're at theta m equals 0. It is maximum and equal to V coil at the skirts, if you will, plus or minus pi over 2. This is insightful because what we start seeing now is that there's a trade-off. There's a trade-off in delivering torque to the motor. We want to deliver torque to the motor, right? But to deliver torque to the motor, we need current. And in order to get current, we have to apply voltage across our R coil. If we don't apply voltage across our coil, then we have no I coil, right? In fact, voltage across the R coil divided by R coil is the actual current that flows. So we need to have a voltage difference here. We need that in order to drive current, in order to produce a torque. But there's this really inconvenient side effect, which is that over here on the skirts, right, this is very lossy. Why is it lossy? Because at the skirts, we note that there is no voltage that is being applied actually to the E-coil portion of the motor. All of the external voltage V coil that's applied is delivered to the resistance of the coil. So you can be sure that at those skirts there is no power being transferred ultimately to the mechanical side of the motor. It is going to be all dissipated as heat within the winding resistance. And this is not good. This is what happens when we have a single winding, single phase DC motor. And this is a significant reason of why we actually have multiple windings in any practical DC motor. Go back and consider this first picture here, the brushed DC motor diagram, and you notice that there is a plethora of windings that are wrapped around on the armature of this rotor. Okay. Now I realize there's some other things going on. We don't have an armature. That's a chunk of metal, and we don't have that in our simple model. But again, the principles are the same. It's just that they get overly, unnecessarily complicated to consider that metal armature initially. So imagine that we could operate our motor. We'll consider this. There is going to be power delivered to our motor only when there is a current flowing from our battery. Okay? So imagine that I had actually a switch. I had a switch that I could open and close, open and close. Right? If I could open and close that switch such that I only applied power in this narrow range right here, let's say. Close switch only in this region. Right? How would I be improving the efficiency of my motor? Well, I would improve it because I would not be wasting power, basically heating the coil resistance in this lossy region that's out, the lossy regions that are out here. Right. Avoids lossy region. Now, actually, a commutator is exactly what this does. And we won't go any further into this at this point, because at this junction we're going to actually really abstract away from this kind of close-up view of the motor and what's going on in the windings, and I'm going to give you a high-level model that is actually simpler than this one, but that hopefully you will be able to appreciate because of having taken a look at a more elemental level through the basic, kind of first principles of the classical physics that's going on in this motor. Okay, so if we look at the original brushed DC motor, you notice that there's a commutator here. That's basically acting as a switch. When the brushes are overlapping that face of the commutator, there's an electrical connection. When the rotor advances and that brush or that particular face of the commutator is no longer underneath the brush, then it's as if the switch was opened and that coil is unpowered, if you will. And so now you have to imagine, I don't have a good diagram to show you at this point, but imagine that instead of having one coil, we had 2 coils or 3 coils. And now we could limit the conduction of each coil to this narrow region that I've highlighted right here. Okay, and of course I didn't mention yet, but there is a trade-off, or there's a loss if we only apply current during this narrow range. We do avoid losing a lot of power to the coil resistance out by the skirts at plus and minus pi over 2. But on the other hand, we are also limiting the range, or the range of the over omega m in which we actually apply a torque. So note that we're not going to be applying a torque over here or over here, no torque, because no current, right? Because no current. So we're not going to end up transferring as much torque and therefore as much power to the output, to the mechanical side of the motor, but we have gained efficiency because we're not wasting a lot of power going to our coil. If we add multiple phases now, multiple windings to our rotor, then we can align those or distribute those such that each coil will conduct for some limited portion of this minus pi over 2 to plus pi over 2. And in that way, each coil operates at a point where it's more efficient, and we also overcome this drawback where the torque is only being applied to the rotor for a limited portion of the plus to minus pi over 2. It in fact will be applied uniformly over the full, not only plus and minus pi over 2, but actually the full 2 pi revolution of our motor. So that's what we get, that's what we gain by having multiple phases on our rotor. Now, I haven't pointed out that even in this single coil motor, at this point, we still would need a commutator if we were going to hope to have this motor spin. You notice that the torque at this point, back to this, let me take all this clutter off here. The torque is positive up to plus pi over 2 and minus pi over 2. But if we go beyond that and we cover the remaining pi of the full revolution, right, then we actually have negative torque. So what we really have going on here is between minus and plus pi over 2, we have the motor acting as a motor. But if we go beyond plus and minus pi over 2, we actually have the motor acting as a generator. If it acts as a generator, what we're actually doing is, notice the torque is negative, and although we haven't developed enough of the model yet, essentially it's going to actually take an effort to spin this motor, and there'll be a torque that will be acting against us, and therefore we're actually going to be putting mechanical work into the motor, and that will be converted to electrical energy, and so we'll actually have a generator function. Problem is here is that without a commutator, every time we go around one revolution, for part of the cycle, half the cycle, we're actually behaving as a motor, so the electrical side powers the mechanical side. But for the other half of the rotation, we're acting as a generator. The mechanical side is actually delivering power, energy to the electrical side. And that's not very productive. It's just a seesaw back and forth. And so we need the commutator, even for the single coil circuit, to basically reverse the polarity of our powering the coil halfway through a rotation. So at pi over 2 and minus pi over 2, it's going to reverse. Now I'll leave it up to you to kind of think through how that will impact things. But what it will ultimately result in is that we'll see a positive lobe over here on either half, instead of being a negative lobe as we see currently. So this would require commutator. All right, that's actually what's achieved with the commutator. Okay, I'm going to stop the lecture at this point, and we will pick up with a second lecture where I will develop much more quickly than this one the high-level model that we're going to use for our multi-phase brushed DC motor.